Okay, now let's do another interesting example about this residue theorem. Okay. Example, show that for a greater than 1, we have integral from 0 to pi d theta over a plus cosine theta is equal to pi over square root of a squared minus 1. All right, so the solution. Very interesting. You see here, we will the theta is from 0 to pi. Cosine theta, that's the real part of a unit exponential number, right? So if z unit complex number, z is ei theta. Ei theta has modulus always 1. Then we know that it is a cosine theta plus I sine theta. And the z bar, the complex conjugate, is equal to 1 over z. This is only works for the complex number with modulus 1. All right? So from here we can get cosine theta is actually z plus modulus of z. This is well, of course, over 2. The relation between the real part and the complex numbers. So it is what? It is 2z. Here is a z squared plus 1. Okay, this is a cosine theta. Then a plus cosine theta. A plus cosine theta, you just add a, so it is a z squared plus 2az plus 1 over 2z. All right, so this is one quantity, remember, we're going to use. In the textbook, the author directly writes the following thing. He say, hence, we have the integral from 0 to pi d theta over a plus cosine theta is equal to 1/2 integral from 0 to 2 pi. We change the bound because we want to get a complete circle, get a closed path. Right? So, okay. This step, how do we know this? It looks like we're going to show, here we need what? We need the integral from pi to 2 pi d theta a plus cosine theta is equal to the integral from 0 to pi d theta a plus cosine theta. We need this result. Is this correct or not? I mean, of course, based on what the author mentioned, it should be correct. Well, let's prove it. This one, the left side, from pi to 2 pi d theta, we kind of shift it, right? So we're going to let u be theta minus pi. We're going to shift it back. U is theta minus pi. So when theta is pi, u is 0. When theta is 2 pi, u is pi. D theta is du. Then theta becomes u plus pi. Theta becomes u plus pi, right? So it becomes a plus cosine u plus pi. Well, if we have this formula, we know that cosine u plus pi is cosine u cosine pi minus sine u sine pi. Sine pi is 0. Cosine pi is -1. So this is negative cosine of u. It's negative cosine of u. It's not like this, right? Well, it doesn't matter we use u or theta, but they are different. Are they equal or not? Okay, so here let's study it. We're going to use the following fact. It's a very interesting fact. This is a very important fact. We integrate from 0 to a fx dx. It is equal to the integral from 0 to a f of a minus x dx. A minus x dx. It's the same thing. You just use u substitution. Let u be a minus x. You can find it. And dx is negative du, but the integral is from a to 0. And that negative sign will flip them. So this is obviously correct. Be careful. It's very important. We're going to use this fact to prove this one is equal to the original one. All right, so let's check the integral from 0 to pi du over a plus cosine of u plus pi. Cosine is a even function, right? Even function means we are going to add a negative number, negative pi minus u. Okay, so cosine will cancel that negative sign. And then I'm going to add 2 pi. Cosine is a periodic function. So I have two steps here. First step, I just add a negative sign for the internal function. I do not change anything. Cosine is a even function. And second, cosine is a periodic function. Add 2 pi. So it becomes pi minus u. It becomes 2 pi minus pi is pi, pi minus u. Pi minus u, you see here, from 0 to pi, from 0 to a, it's a cosine pi minus u, right? It's a minus u, it's a function. So this is equal to the integral from 0 to pi du over a plus cosine of u. We do check what we need. All right, so this is very, very important. Also from another, the byproduct of it is that the byproduct of this computation is that this integral is equal to this integral. These two are the same thing. These two are the same thing. All right, so it's very interesting. From the textbook, you should be able to reproduce every step. If you are stuck, possibly some part you don't see the tricks. Okay, so here this trick is very, very useful and important in the definite integral. Okay, so we do verify that this step is correct. This step is correct, even though it's very short. Possibly the author just thought it's trivial for you. Okay, so we start from here. The whole thing is explanation of it. The whole thing is explanation. Now let's compute. Let's continue this computation. Integral 0 to pi d theta a plus cosine theta is 1/2 0 to pi d theta a plus cosine theta. And it's a closed curve. It's a closed curve, right? So we're going to have gamma. Gamma is what? Gamma is z. Z is equal to I theta. Theta is between 0 and 2 pi, right? Okay, then dz is ei theta di d theta. Ei theta I d theta, right? Okay, so it becomes 1/2 integral along gamma. This is a ei theta is z, I is I, z times I, dz is d theta. So d theta is a 1 over z times I dz. And a plus cosine theta, we did this. A plus cosine theta is here. It's z squared plus 2az plus 1 over 2z. And you cancel this 2 with this 2, you cancel this z with this z, you have another I. I flip it up, it becomes negative I. You flip up to the numerator, it becomes negative I. Correct? All right, so this is the writing in the middle of the solution. And this the gamma is this unit circle. Gamma is unit circle. In this function, this quadratic equation has two solutions. Is equal to z minus alpha and z minus beta. We have two solutions where you just use the root formula. Alpha is negative a plus square root of a squared minus 1. You see, I'm not going to repeat what is the root formula for the quadratic function, but you just follow it, you will get it. Negative no, beta is negative a minus square root of a squared minus 1. Alright, so here this a is strictly greater than 1. A is strictly greater than 1, so this quantity is greater than 1. The modulus is greater than 1. So we get the modulus of alpha is less than 1. The modulus of beta is greater than 1. So one is inside the unit circle, the other one is outside the unit circle. Alright, so from here what we know that this integral along gamma 1 over z squared plus 2az plus 1 dz, of course, over 2 pi I is equal to, this is unit circle, the Winding number is always 1 for the interior numbers. So it is a residue of the this function 1 over stuff with respect to alpha. All right, so what is it? It is supposed to be 1 over alpha minus beta. Remember that it looks like let me compute it here. Residue of f for alpha, limit z approaches alpha, z minus alpha, z minus alpha, z minus beta. You cancel alpha, cancel z minus alpha, z minus alpha. You let z be alpha, so it's alpha minus beta. This is alpha. This is beta. Oh, sorry, subtraction. Subtraction, negative a canceled. So you only have twice. Here's subtraction, not product, my bad. Okay, this is the residue. Okay, so here we put it 2 square root of a squared minus 1, a squared minus 1. And then you move this, what I say? You move this 1 over 2 pi I to the right side, you will get the integral is the integral is the integral gamma 1 over z squared plus 2az plus 1 is equal to pi I square root of a squared minus 1. And then what we need multiply by negative I. So multiplied by negative I here times negative I. Negative I times I is positive I. Positive 1, my bad. So it's a pi over square root of a squared minus 1. So this is the integral from 0 to pi d theta over a plus cosine theta. All right, so we prove this there. The example. This example is very interesting. At least even from the middle step, there are certain integral trick we can learn, and also we get a byproduct this du over a minus cosine u integral 0 to pi is equal to du over a plus cosine u integral 0 pi. They're equal. All right. So, well, let's see if we can show this without using such advanced complex analysis. Let's see if we can really directly integrate, find the antiderivative. For the purpose, let's use a minus cosine. Let's just compute this. Compute this, we will get the same thing. Here we want to say it's called the Weierstrass substitution. For something like this, the interesting substitution, that's something I want to emphasize. There's some like famous tricks we want to teach. So this is called Weierstrass substitution. We let t be tangent x over 2. If t is tangent x over 2, you can compute the cosine of x is 1 minus t squared over 1 plus t squared. Cosine of x becomes 1 minus t squared over 1 plus t squared. And the dx becomes 2 over 1 plus t squared dt. All right, so these are not difficult. You just check it and you can get it. All right, this is yes, this is our cosine x and dx. And then you substitute back. This step, let's ignore this the lower and upper bound. We just try to do the computation. We will have a minus 1 minus t squared, a plus 1 plus a minus 1 minus t squared over 1 plus t squared, and times 2 over 1 plus t squared dt. So here, this is an integral involving the rational and the trigonometric functions. But this point, we only have a rational function. That is the advantage of this Weierstrass substitution. All right. So from here, we just cancel this 1 plus t squared from here and multiply by a. So you will get this integral. Let's not copy it here. It's not important. So numerator is 2. 2, we move it forward. So it's a plus a t squared minus 1 plus t squared dt. That's a multiplication of the denominator. All right, so it is equal to 2 times integral star star whatever. So it's a 1 over a minus 1 plus a plus 1 times t squared dt. All right, so let's have this. So far we got this one. And at this moment, you see a is greater, we also assume a is greater than 1. A is greater than 1. This is a positive number. Of course, this is a positive number. We need to recall some integral formula. A squared plus t squared dt. Let's put t here. It is equal to 1 over a tangent inverse of t over a and plus c. This one is not horrible. This one is a standard formula in the textbook. All right, so we are going to factor out a plus 1 from the denominator. So we factor out a plus 1 from the denominator. Then this integral becomes a minus 1 over a plus 1. This number is positive and plus t squared dt. Okay, so this a, it becomes a minus 1 over a plus 1. Okay, then it is 2 over a plus 1 by the formula 1 over square root of a minus 1, a plus 1. Okay, square root 1 over this number, square root of this number, and then tangent inverse of t over square root of a minus 1, a plus 1, and plus c. No plus c. Now this, let's still put star star. I put a star star because I don't want to change the upper bound and lower bound. I will change it back to x finally. Okay, now let's cancel this a minus 1, a plus 1. You will get 2 over square root of a squared minus 1. Because here you cancel a square root of a plus 1, you have a square root of a, you see, it's a square. You cancel 1, you have a square root of a plus 1 times a minus 1. So 2 over square root of a squared minus 1. And this part, tangent inverse, here it is a square root. We flip it. It's a plus 1 over a minus 1 times t. What is t? T is here. Tangent x over 2. Now I use x. X is from 0 to pi. I use x is from 0 to pi. Okay? We're almost done. Very close. All right. So actually, this part we need to use the limit. This is a improper integral because tangent when x is pi, tangent pi over 2 is undefined, but it has a limit, right? It is undefined. The limit, it's infinite. It approaches infinite. So if you want, you can study this. You can consider this as evaluation of the limit process. Okay, so when x approaches pi over 2 is pi over 2. Tangent pi over 2 will approach infinity. So this is a tangent x. And the tangent inverse of x tangent inverse of x, when x approaches infinity, tangent inverse of x is pi over 2, right? So that's all the stuff we know. So this limit, this part, it is infinity. Here is infinity times a positive number is still infinity. Then tangent infinity is a pi over 2. This is a pi over 2. The first one is a pi over 2. It's a 2 over square root of a squared minus 1 times pi over 2. And second one, when x is 0 is good. It's well defined. The tangent is 0 is 0. See, tangent of 0 is 0. Tangent inverse of 0 is also 0, right? So here you get a 0, and you apply tangent inverse times this positive number is still 0. And then tangent inverse of 0 is still 0. So you get this. So you get 2 square root of a squared minus 1 times pi over 2. You cancel 2, you get pi over square root of a squared minus 1. Again, from here, from this computation, we see that we get exactly the same answer as a positive a plus cosine x. A plus cosine x. So here in this example is very short in the textbook, but in this short example, we actually have a lot of stuff to learn. One thing we need to learn that this trick is important. Right? It is used widely, this trick. And second, we learn this, of course, we learn how to use this, the residue theorem. The third thing we want to emphasize is this so-called Weierstrass trick, the Weierstrass substitution. Weierstrass substitution. Weierstrass substitution just means when you have a cosine x combined with a other polynomials, possibly, especially constant, possibly you will use this t equal to tangent of x over 2. T is equal to the tangent of x over 2. Then you will get the surprising result. All right, you may have the surprising result. This is a Weierstrass substitution. Okay, so we finish this video, and we will continue other examples in this part in next videos. Thank you very much.